Let's get started. Okay, yeah. Okay, sounds good. So, yeah, let's get started. So, I'm Jin. I'm a second-year PhD student at UMSI, advised by Professor Xiaozhu Mei. And today I'm going to present a paper of mine, a recent paper, and some interesting questions I found about in the AI scientist domain. Thanks so much. I'll just get started with a quick poll. So how many of you here have ever had a research idea that you've never had time to develop? Yeah. I think, yeah, because I think as researchers, really, in a lot of cases, we have some random ideas. We look at some papers, we go to a poster session to say, oh, maybe we can do this, we can do that. But we really end up never get the amount of time that we need to develop that idea. So that motivates this paper called Idea2Plan, exploring AI-powered research planning. And I'll probably spend about 45 minutes on the first part about this paper, and then I'll share some bigger lessons learned from the AI scientist literature. Okay, I'll just give a big shout out to my managers at MSR. Without their help, I probably could never finish this piece of work. Okay, so let's get started to...
sorry.
Yeah.
There's a message said in chat says no sound.
Should I move this over?
Oh, and someone else has no issue.
Okay. I see. So yeah, I think it should be fine. Yeah. Can you guys hear me now?
Yeah.
Okay, sounds good. So let's go to the motivation part. Transforming a research idea into a research plan requires a lot of time and cognitive effort. Usually, we have this iterative process of developing a research idea. We start by, okay, now we have this idea. We go to Google Scholar or Perplexity. We review prior works, find relevant papers, and then we formulate our hypothesis. And then we select appropriate method to verify this hypothesis. And then we design experiments that we need to do. And we do this, it's not like one single run, it's more like iterative process. After we design experiments, when we notice something might be wrong about a hypothesis or something about the method we choose. So we go back and revise our hypothesis and go through this pipeline again. We refer to this process of turning a research idea into a concrete testable plan as research planning. And why research planning is important? So the reason is that we want to investigate how AI system can transform research idea into a research plan for several reasons. First of all, from a scientist's perspective, scientists really generate more ideas than we can actually execute. And a capable idea-to-plan system could help scientists make better progress in their daily research. And second, from a collaboration perspective, scientists could benefit from a structured document that put everyone on the same page. For example, if I have an idea, it's better for me to put it on for example, on a Google Doc to see, here's my hypothesis, here's the method, here's the experiments I want to run, and share this with my groupmates so that we can discuss. And third, from an AI scientist perspective, research planning skill is an essential skill for developing autonomous research agents. For autonomous research, we're referring to the kind of agent that can independently come up with hypotheses, design experiment, run experiments, and refine its hypothesis. So research planning is an important stage in this pipeline. So how do previous works evaluate AI systems for research automation? Broadly speaking, we can categorize previous efforts into two parts based on their output form. The first part is paper level evaluation. Basically, the final output of the system is to generate a research paper or research proposal. And previous papers usually evaluate this research paper, for example, using like a peer review form that, for example, the reviewer get when they're reviewing a paper submitted to like New York ICML, and they get evaluated by like novelty or like whether they're for example, from like 1 to 4, 1 to 4 Likert scale. And the second category is code level evaluation. The system are judged by their ability to produce either code implementation or the experimental results. This code implementation can be as small as a single function, and more recently, the evaluation target becomes more complicated, like can be evaluated on a full code base. And more recently, not just implementing, giving the code and without actually running it. A recent paper called Paperbench for OpenAI. What they do is that the agent is challenged by taking a paper as input, and the agent is challenged to reproduce the whole code base as well as the experimental results from scratch. So as you can imagine, it's actually a pretty challenging task. So think about if you are given a paper from some spotlight oral paper from a top machine learning conference, probably, I think for me, it took me at least a week or more to reproduce the full code base. And as shown in that paper, this turns out to be an extremely challenging task. Even the sorted model cannot achieve a good performance, like around 20%. So here is what previous works have done for evaluating like these research automation systems. And in terms of research planning, actually research planning is kind of overlooked in the previous literature. The most relevant work to us is the first one is called Code Scientists. They proposed a full pipeline for autonomous AI scientists. They only included research planning as an intermediate step, and they didn't provide any explicit evaluation for that. The other work called machine learning research bench, they do evaluate research plans, but only on high-level dimensions such as clarity and novelty, and give it like a, for example, 1-5 score. And the model they use is also a language model as a judge. Okay. So the takeaway for this page is that previous work evaluate the evaluation mostly overlooked the research planning, but research planning is actually a very important bridge between ideation, where the system come up with an idea, and the final, actually the second part, the code implementation part, because before you actually code up your repo, you need to define what are the experiments you're going to run, right? Like to define what are to do for this project. Okay, so what is the research plan? So research plan serves as a roadmap for executing the project. In our work, we focus on AI research, and we adhere to the common structure of research plan for AI papers. So this is like the structure of the research plan that we use. We have the introduction, which contains background, primary objectives, research questions. We have the key literature section, and then the method experimental design. And lastly, the resource components and ethic considerations. Just a footnote, we also discard any plan components, for example, like timeline or logistic or human expertise, because those are very dependent on the actual team, the team of research that work on that, and cannot be easily determined by language models. Okay, now we have a definition of the research plan. Then we need to think about how we can evaluate how an AI system can do idea to plan this transition. So basically the idea is going to be the input and the research plan is going to be the output. The question is, how do we get high quality research idea and research plans? The high level idea is that we propose to collect research ideas and reference research plans retrospectively from papers. There are two data selection criteria that we think are useful for the desired idea and plan pairs in our case. The first thing is training data independence. We want that idea and research plan are free from any potential leakage or contamination from the training data. For example, if my research idea is implement transformer and I give this idea to GPT can, because it has seen the paper already, it can directly fetch from its parametric knowledge like just to tell me exactly what they did in the paper. Then it becomes not very meaningful to evaluate the model on this because it's simply testing this memorization of that specific paper. So we do want the idea to be out of the training data. And second, ideally we want the idea and the plan and the paper that we extract them from to be high quality, so we can test some not some trivial ideas, but rather some idea that require a careful design. So the proposed sauce here is that we choose ICML 2025 Spotlight and Oral paper, because the good part about this is that the data cutoff, the submission time of that conference is February 2025, which is past the data cutoff of the language model that we've tested. And further, we also filtered out any paper from this set that has a preprint before that date, just to make sure there's no possible contamination. We randomly sample 200 papers as a health test set, and also around 30 papers as a development set to develop our system. Okay, so here we are. We start with this set of SML paper, and then we use language model to extract the research idea and reference research plan given the full paper of this set. Here is an example of a research paper, of a research idea. The paper is called Jailbreak Text, How Useful Are Your Jailbreak Outputs? And this idea is extracted from the abstract of this paper, which is a spotlight paper of SML 2025. We also extract the reference research plan. This is we only show like one bullet of each of the sections. For example, in the introduction, it contains like discussing the background about language model are protected by this safe guardrail, but this adversarial jailbreak can break this outputs. And in the key literature side, it referenced like relevant literatures and why that matters. In the method, it contains, for example, like baselines or potential like SFT strategies for jailbreaking. And in the experiment, it shows what are the experiments that actually done in that paper. Okay, and in the resource analysis, it contains considerations about what are the possible ethical considerations, etc., etc. Okay, great. Then we have the input, and this is not necessarily output. I will explain later. But we have the input, which is the research idea, and this serves as the input to either a language model simply prompt it, right? We say this is a research idea, and we want this structure output. Please give me the research plan, or we give it to an agent which have an access to external tools like searching over or read archive papers. Like specifically, we give it these two tools. The first tool is that the agent can generate a query. It can say, okay, the idea is about jailbreak. I want to search about jailbreak large language model benchmark, for example. And the research tool will return a list of archive papers with their title, abstract, and archive ID. And this part we limit to up to 10 papers per search. And the other tool the agent can call is that, for example, it may search over a bunch of papers and say, oh, maybe this paper is most relevant, so I want to read it in depth. So the agent can say, I want to read this paper, and we are going to return a paper summary of that paper. Okay, so up to this point, we have the research idea, and we give it to either baseline or agent, and they give us an agent-generated research plan. We also have this reference research plan extracted from the full paper. The next question is, how do we evaluate, right? Because this document can be long, like can be pages long. How do we evaluate how agent-generated research plan like reflect from the reference research plan that we extracted from the full paper? One of the key challenges here is that a single research idea can lead to multiple equally reasonable research plan. Because the input is a research idea. If the research idea is about jailbreaking attack, a new jailbreaking attack method, for example, the output research plan could reasonably choose different jailbreaking data set, different like black box model, white box model, or different evaluation matrices. So those are all valid design choices. If we think about the most simple way of evaluation that we directly compare, like compute a similarity score, for example, between the two long documents, it might actually miss a lot of these nuanced design choices. For example, if they actually choose a different set of data set, but they are not sharing like semantically close enough, it didn't end up with a high evaluation score. So what we propose here to counter this challenge is that we adopt the rubric-based evaluation approach. Basically, we take the reference research plan and turn that into a rubric, and we hope that those rubric questions could identify high-level design choices that should be addressed in any reasonable research plan for the given idea. To just give a visual illustration, we start with this research plan, and we turn this, for each section, we turn this into a list of yes or no questions. For example, in the introduction, we can ask, does the plan state that virtual attacker can bypass language model guardrail as a background? And in the literature part, we ask, does the plan cite this paper jailbroken or similar work on manual prompt engineering jailbreaking? And in the method, we can ask, does the plan describe the system prompt alignment method that simulates mobile refusal via instruction constraint? And in the experiment design, we can ask, does the plan propose experiment that evaluate both jailbreak success rate and post-jailbreak utility on objective benchmarks? So in this way, we do not need to compare like two fixed plans because there might be variance in terms of design choices. We can use these questions to grade any generated research plan against this rubric. Basically, for each of the question, we look at the question, look at the generated research plan, and we give it a yes or no grading of that question. And in terms of the final matrices, what we do is for each of the section, we simply count the percentage of yes, the question actually graded at yes. So this gives us a score from 0 to 1. And for the overall score, we simply average over the 5 sections. Great, and this gives the final piece in this figure. We generate the grading rubric from the research idea and reference research plan, and we compare that with the generated research plan. Okay, so this is a major pipeline, but as you can see, in the generation of idea and reference research plan, we use language model. In the generation of grading, we use language model. And later, actually, in the evaluation, we use the language model. So we do need some human study to see how good this pipeline is. We ask 2 questions here. First, how do human experts rate the quality of AI-generated research plans and evaluation rubrics? And second, how does a language model as a judge align with human expert grading? For the first question, what we do is that we recruit 8 human experts to grade the generated research plan and rubrics on a 1 to 5 scale, 1 to 5 Likert scale. The topics covers computer vision, NLP, AI for science, and graph ML. This is the beginning part of the guideline that we provide to the expert. So basically, we are asking them to evaluate 2 pieces of language model LM generated content. First is the reference research plan that generated from the full paper. We ask them to evaluate how well the AI extracted plan captured the original paper's content. And for the second part, we give them the rubric questions for each of the section, and we ask how good are the AI generated evaluation questions for assessing this research plan. And in the second part, we also give them the research idea and ask them to consider, if we develop a research plan from that idea, what are the reasonable rubric questions that should be asked to assess the research plan. And here are the results. So we're given a 5-point Likert scale. 1 means major issue and 5 means well done overall. And we noticed that for both the generated plan and the generated rubrics, and for on all of the sections, we get a overall score of over 4. And this suggests that the extracted research plan and rubrics are of reasonable quality. Okay, and let's move to the second question. How well does LM as a judge align with human expert grading? And just to give a sense of the evaluation we're thinking about, this is the full rubric for the paper I just shown, the jailbreak text paper. So each of this in this brackets cover is like one rubric question. So this means that we're thinking about like tens, like maybe 50 questions for one of the papers. So this makes human manual grading like prohibitively expensive. So that motivates us to use a language model as a judge. Also, for example, in the paper bench paper from OpenAI, they also use a similar method to basically use a language model as a judge to grade, in their case, a generated code base to a grading rubric. But in our case, it's a generated research plan. What we do here is that for 10 generated research plan, we randomly sample these research plan from the development set of our paper. We manually grade them against the respective rubric. Basically here, we have language model, take the rubric, take the plan, give a grading. We also have a human expert, ask them to look at the rubric, look at the generated plan, and give a yes or no question for each one of the question. In this way, we get the ground truth grading from human expert. Since each of the question is a yes or no question, a binary classification question, we can evaluate the language model's grading in this by binary classification matrices. Here is, we call this dataset the Idea2Plan judge eval. We try different language model as a judge here on the first column. We also report binary classification matrices like accuracy, precision, recall, and F1 score. And the last column shows the cost of evaluating one research plan against the one rubric in terms of dollar here. That's the last column. So what we see here is that O4 Mini overall achieved the best F1 score in terms of grading compared to human experts grading. And surprisingly, even the weakest model, the GPT 4.1 Mini, achieved a very good F1 score in this judge eval benchmark. In our later study, in order to get the best possible performance, we use O4 Mini. Oh, and by the way, the O4 Mini with reasoning effort set as high. We use this choice for all of the evaluation in our study. Okay, so these concludes the first two parts about the verification of the system to see how well, first of all, how's the quality of the AI generated research plan rubric, and second, how well are our language models adjust perform on grading compared to human experts. I want to maybe stop here a bit to see if there are any questions up to this point. Yeah.
So going back to the chart with like the using the experts to judge how well the LLM plan was.
Yeah.
Can I ask why you guys did it? Something that I would think about is maybe seeing if like having a human also create a research plan and then having these experts rate the human's plan in comparison. Is that something you guys consider?
You mean, is that like the purpose is like comparing how human as?
Yes, yeah, because maybe these experts would give like 5s for everything that the human created, but 4s for everything that the LLM created.
I see. So basically comparing how good how human can extract the research plan versus LLM.
Sure, yeah.
Yeah. I think this is a good question because what's the missing picture here is that this is how language model can do, but how human can extract the research plan. But one of the reasons that we didn't do that is if we think about this task, the human do not need to write a bunch of text. They only look at the language model generated plan, look at the paper, and we ask them to select the paper they're familiar with, so they don't need to actually understand that paper because they already are familiar. So they only need to give a 1 to 5 score and also some short comments on that. So this is like a more like easy or like low effort task for them.
Okay.
So to answer the question, one of the reasons is that ask him to generate a research plan which contains pages of, So But I do think if we do have the resource to do that, that will add, I think, important message to this to compare to human how well our system can generate research plan and research rubric.
Thank you.
Okay, thank you for the question.
Do the annotators already run the SML papers?
For this annotation, we didn't select from SM.
Oh.
So actually, what we do is that we first recruit them and we say choose one of the paper that you are familiar with in their respective domain. And then we take the paper, we run our system, we generate the research plan, and we give it back to them.
But I wonder if that's going to introduce a bias, because if the annotator is familiar with that paper, and if the system does not generate rubrics or the plan that's consistent with the original content from that paper, like whether the annotators will give like a low score because like it's not consistent with the original content.
For the generated plan part, the reference plan, the plan should match.
Okay.
So for that part, in the for example, in this there are some like more detailed guidelines here, but we're basically asking the evaluator how this captured original paper's content.
Okay.
Intent. So that part, if the system does not do a good job, should be penalized.
Okay.
But for the second part, for the rubric question, because the rubrics are intended to be like high level, so that they can capture different research plan generated from the same idea. So for that part, we do have like a more detailed guideline to see, do you think it's a reasonable question to be asked to evaluate research plan generated from the idea? Does that answer the question? Like, I think the two-part evaluation is a little bit different.
Yeah. And I wonder, what is the actual comment from annotators?
Yes, that's a very interesting question. In some of the paper, what we get is that we use overall meaning throughout the study, and one of the bias we see is that it sometimes does not have a sense of a big picture of generating the research plan. For example, if I'm given a paper, I'll probably start with, why we design the whole 3 experiments. They probably serve like 3 purposes, and together they solve a whole large purposes. For example, like showing that my method is better than baseline, for example. But overall tends to focus on some of the details first, and just listing the details of the experiment design like very detailedly, but does not have a sense of like big picture of why we do this. So these are the comments that we get from the comments that they provided in the evaluation.
That's interesting.
Yeah. Okay. Sounds good. So that will conclude the part about the design of the system, the design of the benchmark specifically. And then let's go to the baseline and agent design. We test a few baselines here. The first is what we call a naive baseline. This is a one sentence prompt, a single prompt, generate a detailed research plan. So the reason we include this baseline is try to mimic the simplest scenario where me as a scientist, I log into ChatGPT and I put, give me a research plan. Because I, as a user, I probably wouldn't write down a very super long like guideline. And additionally, we provide a section template, only the titles of each section, to ensure a consistent format. The reason we do this is that without this section titles, we notice the language model start to generate non-relevant sections like timeline, logistic, which may lead to them waste some of the token on those part and may unfairly affect the evaluation. So that's why we include the section templates. We also include this zero-shot baseline. It is the naive baseline plus some general guidelines like analyze the research idea thoroughly, things like that. We also have this one-shot, basically zero-shot plus one example research plan. These are the first 3 will be the simple baseline that we test. This is only one run of prompt, like no external knowledge. For the agent part, we use a simple React scaffolding. And React, I think, so far is the most widely used agent framework. We didn't make any change. We used the vanilla version, the sought action observation. So for those of you who might not be that familiar, basically the agent can say, I want to choose this action. For example, I want to read a paper. I want to search over something. And we will call an external tool to actually do the search or do the read. and give it back, and the agent will have the full conversation history and to decide what's the action to be done next. And just some more information about the tool part. For the search tool, the input is an agent-generated query. The output is up to 10 archive papers with their titles, abstract, and archive identifiers. In implementation, we use Bing Search to serve as a search engine. For the archive read tool, input is an archive ID. The output is a paper summary generated by O4Mini from the full paper. We limit the number of search and reads to 5 each, so the agent can at most call 5 times of search and 5 times of reads. Here is the evaluation across a set of open source models like Phi, DeepSeek, V3, DeepSeek R1, and a series of GPT models. For each of the model, we have 4 bars. N denotes naive. 0 shot means 0 shot. We also have 1 shot and react. We also include this green line called upper bound. What we do is that we simply give O4Mini the full paper and ask it to generate a research plan. And we compare the research plan towards the rubric that we generated. So this serves as an estimate of the highest possible performance on our evaluation. The reason, I think one of the understandings is that we couldn't expect to generate an exact rubric that can fulfill any of the rubric questions. So we do have this like empirical upper bound here. Okay, so like some observation from this. So first of all, we do notice that GPT-5 and GPT-5 Mini and GPT-5 achieved the best performance compared with all other models. Another observation is that for the React agent, only in some of the models we notice this React agent, which should be more powerful because it has access to external knowledge that like we might expect it to improve the performance over baseline, but only on GPT 4.1 Mini and GPT 4.1, and maybe GPT-5 Mini. There's only like I think a few percentage of improvement here. That we notice that React actually improved the performance. So I will have we have a case study on the next slides. But I want to stop here to see if there are any questions or comments to the evaluation. Okay, let's take a look at what are some of the cases that this React agent, which can search and read over archive paper, can actually get a worse performance. So in this part, this is the ground truth of this paper. This paper is on prediction policy, and this is the literature review section. They have one important citation, which is this paper called Prediction Policy Problem from John Kleinberg. So this is one of the foundation work in this domain. That's why they cite them and use them to develop their method. And if we directly prompt GPT-5, so we know external knowledge, GPT-5 can correctly identify this paper as an important citation. But however, what we see if we give GPT-5 the choice to search and read over external papers, we see that it actually missed this citation. So we think this reflects the conflict, a long-standing conflict between parametric knowledge, which means the knowledge stored in the model's parameter. For example, like in this case, obviously this paper is in the training data of GPT-5, and it actually identified this citation correctly, versus the retrieved knowledge, which we usually see in the RAG system, where the system can retrieve a large amount of external knowledge, but need to make a decision about what are the actually important or the most relevant information here. For example, as you can see, the cited paper for the React agent are actually more recent papers, but more focused on some specific model design, rather than this like foundational work in the domain. But since the focus of these paper is not like new algorithm design, these paper are less relevant. And we highlight this like conflict in our paper. But in our paper, we didn't propose any further like agent design or training pipeline to mitigate this. But we do think it's something that's worth noting. Okay, so I will briefly go through some other experiments that we did. These are in the paper, but I don't think I'll have time to go into details here. The first is the lens research quality analysis. We observed GPT-5 and GPT-5 generate a research plan that are 2 to 3 times longer than, for example, other like overall meaning or GPT 4.1. So after controlling, to investigate this, we controlled output length. The method that we used to control the output length is very simple. We added 1 sentence prompt to say, please control your output under a specific number of words. So this is like soft control. It's not like a hard control that we truncate the output. But this, empirically, we find that this to be a very effective way to control the verbosity of the model. And after controlling this, we find GPT-5 and GPT-5 mini still outperform other models. So which means that the reason we see they're outperforming other models is not simply because they're generating a longer research plan that may hit more rubric questions. It's also because after controlling the lens, they're still generating a better plan. Another thing we do is that starting from the case study of the React, we noticed that if the agent retrieve only weekly relevant papers, they may actually hurt the performance. We want to see whether created directly relevant papers instead of retrieve one can improve the model's performance. So we extract up to 3 like most relevant papers for each paper, and we directly give it to the React agent. And we noticed that this consistently improved the model's performance, ranging from 0.3 to 9.9%, especially for mid-tier model like GPT 4.1. The last thing that we tried is, okay, we built this benchmark. We have some observation about the model's performance. If we want to further improve the model's performance on this, what are the natural training strategy that we can try? One way is that we have like an infinite amount of like research papers published before, like millions of papers. Can we use those research papers as training data for our system to better generate the plan? We test this hypothesis by collecting idea and plan pairs. The idea serves as input and plan serves as output for ICML 2024. And we SFT GPT 4.1 mini and GPT 4.1 on this SFT dataset. And we noticed that this training actually slightly reduced overall performance. And we also observed that the fine-tuned model tends to hallucinate more in this case. So this actually corresponds to some recent literature analyzing if you SFT on some questions involving knowledge that are not in the pre-trained data, these actually encourage the model to hallucinate. So we do think this observation also are very relevant to that line of research. Okay, so as the conclusion, our contributors are we formalize this Idea2Plan test and we build a dataset from post-element cut-off AI papers. We build a pipeline to automatically generate rubric for generate rubrics for research plans. And this also gives us a way, like later we can easily iterate to a new set of papers that are beyond the future model's data cutoff. We also conduct a human study to show that extracted plan rubrics are of high quality. We propose this, and third, we propose the LLM-based judge and Idea2Plan judge eval to compare language models judge with expert annotations. And we discuss experiments and results with several SOTA LLMs on the different prompting and agentic strategies. Okay, sounds good. So these will conclude the first part of this presentation about this specific paper. Are there any questions or comments or?
For the continued training, did you just, for the GPT models, did you just use like the pre-training fashion or, supervised one too?
Yes.
Okay.
The input is the idea, output is the plan. So, because GPT have the API for, you can upload the dataset and it automatically train SFT for you. But I don't think they have an API for pre-training stage, like pre-train GPT model.
do they did you do hyperparameter tuning for that as well?
So what we do is that we use that fine-tuning service also on Azure, and it has automatic.
So it doesn't allow you to tune the learning rates or something?
It has a default choice of automatic tune the hyperparameter for you.
I see.
And we directly use that. But alternatively, we can also set a fixed number of batch size, learning rate. But from our end, we don't know the best hyperparameter, so we directly use that automatic hyperparameter tuning.
Yeah.
Okay. Okay, sounds good. So I will spend the last probably 50 minutes to discuss, just to take a step back from this specific paper to this domain of AI scientists or AI for scientific discovery. In the past, I think past year, we're seeing increasingly evidence from Twitter or some other blog posts about how this SOTA model can help scientists make scientific discovery. Ernest is a professor, math professor at UCLA, and recently he posted about how he used ChatGPT to solve an open problem in context optimization. Also, a bit earlier than Terence Tao had a blog post explaining how he was able to use GPT-5 to help improve, prove a part of his proof for a math question, which involved finding some numerical parameter verifying a certain quality to build a counterexample. From an industry perspective, Kevin Wells is the VP of OpenAI, and they launched this initiative called OpenAI for Science. And the goal is to build next great scientific instrument AI-powered platform that accelerates scientific discovery. And they've already made some blog posts about how they can use the GPT-like model to formulate some biology questions, and they actually collaborate with the wet lab to verify that. Another example is Williams Values is a vice president of OpenAI on post-training. He recently left OpenAI and to start a startup on this. Let's say our goal is to create an AI scientist. So I think the takeaway is that increasingly we're seeing more and more interest in this domain to build something that can do research by itself. But today I want to talk about I think two bigger lessons I found on this domain. The first part is the claim on novelty, or the claim on GPT-5 can do independent scientific discovery, these kind of things. This blog post is from Sebastian. He was a vice president at Microsoft, and he then moved to OpenAI. And in October, he made a blog saying science acceleration by AI has officially begun. Two researchers found that a solution to 2-year-olds' problems over the weekend with help of GPT-5. And this triggers a large amount of reposts to say, oh my God, GPT-5 can do scientific discovery, mathematicians are done, these kind of things. But this actually a not very accurate statement, because what actually happened is that GPT-5 found the solution proved by someone else, maybe 50 years ago in some of the textbooks or research papers. So it does not solve the problem, it found the problem. So this, and later triggers a large backfire, a lot of people repost to say this is not accurate. And Sebastian ended up deleting that post and say, oh, my post last week created a lot of unnecessary confusion, blah, blah, blah. And to explain that actually there's not discovery, rediscovery something that people proved before. So this highlights the nuances about claim on novelty, about truly discovery, true discovery made by AI systems. This is more of an example from industry side. Another example is from academia. Okay, Sakana AI may not be their industry lab, but they have a paper, I think 2024, called AI Scientists Towards Fully Automated Open-Ended Scientific Discovery. This also gained a lot of momentum on social media. In their paper, what they claim is that their AI system can perform research independently and communicate their finding. We introduce AI scientists, we generate novel research idea, write codes, execute experiments, visualize results, describe its finding by writing a full scientific paper. And notice how they describe that, like genuinely novel research idea. But however, later, about a year later, there's another paper called All That Glitter Is Not Novel, Plagiarism in AI-Generated Research. This paper looked closely into the research paper generated by AI scientists, and they find that the experts identified 25% of the 50 evaluated research documents to be either paraphrased or significantly borrowed. An additional 32% of ideas are partial overlap with prior work, and only a small fraction to be completely original. And this paper was an outstanding paper at ACL this year. So I think this is another example about it's actually these days with all the coding tools and large language model, it's super easy to build a pipeline that can do some retrieval, do some generation of idea, and write some code. But the real problem is actually on the evaluation. How do you know the idea is not some like paraphrased idea from some previous work that are actually novel? And how are you sure like you can make this claim that the AI generated idea are actually novel? So I think this is like the first beta lesson I want to talk about. The claim on novelty is actually pretty hard, and evaluation turns out to be in my opinion, the hardest task for AI scientist systems. Okay, and the second part, what I want to discuss, I want to start from this post from Sam Altman. So what they say earlier, like October 29th, what they say is that we have an internal goal of having automated AI scientists in AI research in by September 2026, and we want to have true automated AI researcher by March 2028. And in the red box here, in 2026, we expect to have that our AI system may be able to make some small new discovery. In 2026, we could be looking at big ones. So this is a surprisingly detailed timeline, right? 2026, 2028, and they want to make like truly automate AI scientists. So this makes me, I think, an interesting question for me to think about is like, what's the future of researcher, right? Like, because these days, like this AI system are so powerful that they can do math, they can do coding probably better than all of us, like any human being. And probably later, one single system can do all of them, like biology, physics, math. And then maybe we're entering like a possible future is that the AI scientists are making more and more scientific discovery, and they just come back to us to say, oh, I made this discovery, I cured cancer, I solved like P is not NP, whatever. And for human, we don't even have the time to verify that. And for some of those questions, probably we wouldn't even understand their solution. And some interesting question I like to think about is, for example, like if we could launch maybe 2 years later, right? OpenAI can have this AI scientist for sales. We can simply rent 1,000 AI scientists to run a specific research problem. And we launch those AI scientists and come back with thousands of discovery. How do we first like verify those results are trustworthy? And second, how do we even understand? Because as human, we do have a low like capacity compared this parallelizable AI scientists. And actually, when I think about this, it's actually not that far from the reality, because for example, if you use like Cloud or Codex, you can these days you can delegate like sub agents that run fully autonomously on themselves, and they come back, run the code base, come back and tell me, oh, what they've done. And similar question are here, right? How do I know the code or conclusion they derive are trustworthy? And how do I even understand if I don't have the time to walk over like thousands lines of code? Yeah, I just want to make a point that this is not pure sci-fi like imagination. And the second question I think is like, what are going to be a good interface for like AI scientists collaboration? Because from the two challenges I noticed here, we do need something that should better ensure trustworthy and help us understand the result in a comparatively low effort. Okay, sounds good. I'll probably hop here to see if there are any comments or like brainstorming or like, yeah.
I think for here, I don't think evaluation is necessarily harder, because just use your example of like using the code agent to do the scripting for you. You just run the code in the sandbox and see whether the results will match your expectation. So I think there might be some tricky ways to, build a sandbox and let the AI execute this plan or something and see the outcomes, and then we can understand how good they are in terms of helping the stuff. And in terms of like the bigger lesson, I feel like this is just my perspective. I feel like we might be a bit more critical for the AI on the novelty part, because just look at us. Look at the guy who invented the LSTM, who always shouted that Jeffrey Hinton stole his idea for the neural network, for all of the things, like the attention mechanism is invented by him or something. I mean, there might be a point, I don't know, I didn't read his paper carefully, but it might be just a good paraphrasing, who knows, right? Because, yeah, I mean, and also just look at other disciplines. I think for the, in biology, like for the DNA, I think his idea was not found until like the next century or something. So I feel like a better way of retrieval and a better framing of the idea they found in the retrieval process is still valuable.
Yeah, I agree.
Yeah. So, and also like, for the novelty, I feel like even for us, serving as reviewers for a lot of top conferences, I mean, how do we even judge the paper on novelty? Like, I feel like, I don't know. I do not have a standard in terms of like judging the novelty of the papers nowadays. Yeah.
For me, when I think of the whole novelty issue, the first thing that comes to mind is explainability. Like if we can really work on understanding why the model comes up with what it did and what pieces of training data it did to look at its outputs, then we can really understand if it's purely novelty or if it's just paraphrasing.
Yeah, I agree. To answer that question, I think what I try to make the point here is about like we should be cautious about the mindset of claiming novelty and to make a headline for because there's an incentive to.
Yeah, but just look at all the scientific papers submitted to the ACL, IQ. They all claim that we are the first in doing something.
Yeah.
Do you really believe that we have so many pioneers in this field? Because I don't know. I might be more like, I don't know.
Yeah, I agree. I agree. Yeah, human are also like because they're also incentive to overclaim a bit.
Yeah.
To end up being accepted.
Yeah. And I don't know, maybe because the language models are trained on the humans' data, so they probably pick up this pattern from the human scientists as well.
Yeah. Which is a bad. Which is a bad, in my opinion.
Yeah.
How do you foresee like your system like being used in the future? Like, do you foresee it as part of like the collaborative system? Because your system currently is only like the agents doing the work.
Yeah, that's a very good question. So, I personally, I'm more thinking about maybe it could be a component to evaluate and developing better AI-centered systems. But in the end, I think some human supervision should be put on the top of that and even actually for any of the system right now, we didn't see anything that can be truly autonomous. So there must be some human knowledge guiding, okay, you should solve this problem because we think this problem could be solved by this system. I do think both parts is more important, but for my research, I'm more thinking about the first, like as developing a system. Yeah. Okay, thank you so much for the questions, and thank you so much for coming here.
Thank you so much for your
Yeah, and thanks for everyone that's online. Okay, bye-bye.